All right, I'm going to take you through a whole bunch of free body diagrams and then equations. So I have 5 pictures here, and I'm going to do a couple more. But this video is going to be just about like how forces are going to affect just a single object. So all of these are just boxes. Okay, so this is going to be a box on a ground being pulled horizontally. That's an FA. That's an applied force. Box on a ground being have an applied force up. Applied force at an angle, applied force from a box on a wall, and then a box on a wall with an applied force at an angle. So this is just kind of some variations of what we'll do. And for all of these, I'm going to draw a free body diagram, and then I'm going to break down their forces. Okay? A free body diagram is just a dot and then the associated forces on that particular object. Okay? So we have a box on a ground with some applied force to the right. So it's pretty clear that we have some applied force this way. We have the weight of the object, which is equal to mg down. We have the normal force of the surface pointing up, and then we do have friction that will be pointing backwards. Okay, so those 4 forces are the forces acting on that box. Okay, so now we need to break them down into their pieces. So we're looking just at the x direction. We have the applied force is going to make it move to the right. Friction is going to oppose us, and that may or may not cause an acceleration to the right? This acceleration is in the x direction. And it's pretty simple. If the applied force is bigger than the frictional force, then you have a net force in the x direction, which will cause an acceleration in the x direction. Right? In the y direction, we have the normal force up, and we have mg down, and that's going to equal 0. We know that's equal to 0 because the acceleration in the y direction is 0, so the net force in the y direction has to be 0, meaning the normal force balances out mg. Okay? And like all of these questions, we know that the force of friction is going to be replaced by mu times the normal force. And in this particular example, we know that the normal force is equal to mg. So we can take that top equation and actually write it as Fa minus mu mg equals ma. Again, the maximum frictional force is equal to mu, which is the coefficient of friction, times the normal force. The normal force in this case is mg, and so then we get that equation. Okay, and what it says is that the applied force is bigger than the frictional force. That net force will cause the mass, which is how we quantify inertia, to experience an acceleration. Okay, all right, let's do the next one. We have a box on the ground, and we have some applied force pulling up. Okay, so we have some applied force, which is up. We have gravity, which is down. And then we have the normal forces, which is up. Okay, there is no forces in the x direction, so we don't have to worry about that. And then the y direction, we have the applied forces up, the normal force is up, mg is down, and that equals ma. And again, we're not really even sure that might experience an acceleration, so we have to go through all these different cases. What would happen if the applied force all by itself was bigger than mg? Well, that would cause a vertical acceleration, and it would also cause the normal force to go to 0 because, well, the box would be lifted off the ground. Right? The ground can't apply a force to the box unless it's sitting on it. But what if we had this scenario? Okay, let's say we had an applied force of 10 newtons. Our box had a weight of 40 newtons. Okay, well then, if you only pulled up 10 newtons and it weighed 40 newtons, you're not going to have an acceleration. And then what would the normal force have to be? Well, then the normal force would have to be 30. 10 plus 30 minus 40 equals 0. So what did the applied force do? Well, if you apply a small force up, it's going to reduce the normal force. Well, if you keep increasing and increasing and increasing the applied force, eventually the applied force will be bigger than gravity's force, and then it's going to accelerate up. Okay, so pulling up on a box is kind of pretty easy. Okay, now let's pull at an angle. And so it's one of those things that if you pull at Fa, and that's your angle, part of your force is pulling to the right, and part of your force is pulling up. Again, so your applied force is this way, but really, part of it is pulling it to the right, and part of it is pulling up. If this is the angle, and this is Fa, This is FA cosine theta, and this is FA sine theta. So when we do our forces, there's the applied force, normal force, gravity, friction. In the x direction, we don't have the entire applied force, right? It's pulling up and right, but we do have FA cosine theta to the right, and we have friction to the left, and that equals MA, and that A is in the x direction. And then vertically, we have this piece, right? We're pulling to the right, but we're also pulling up. The up part is opposite the angle, so it's the sine theta. We have the normal force, and we have gravity. And let's assume that when we pull this box at an angle, that the box is sliding across the ground, so there's no vertical acceleration. Let's be clear, we could have a big enough FA such that we actually rip this thing off the ground and cause a vertical acceleration. But in this case, we're not going to, okay? And if it did lift off the ground, the normal force would equal 0, right? If the vertical component of the applied force was bigger than mg, well, then you'd have liftoff, okay? And we're going to do roughly the same thing we do on all of these things. We're going to take this equation and solve for the normal force. If you look at the y equation is going to tell us that the normal force is equal to, we'll add that over, minus FA sine theta. Now we know what the normal force is, because up here we're going to take the force of friction and replace it by mu times the normal force. So we're going to take this guy and put it in the normal force, and then we're going to get some big equation. We're going to say FA cosine theta, that's the horizontal force due to the applied force, minus friction. Friction is mu times the normal force, mu. The bottom equation tells us that the normal force is mg minus FA sine theta, and that's going to equal ma. Now go ahead and plug in all your numbers to find the acceleration. Okay, so horizontal pull, vertical pull at an angle, they're all very similar. Draw the free body diagrams, break them down into their components. We typically use the y component to find the normal force. Once we know the normal force, we can replace the force of friction by mu times that normal force. And the normal force in this case is this. The normal force over here, it was just mg. And the normal force over here, well, it kind of depended on how hard you pulled. If you pulled harder, you reduce the normal force. Okay, let's look at these two scenarios. Box on a wall, easier version, pushing straight, harder version, pushing at an angle. So let's say we push straight, okay? Let's do our free body diagram. So we have some applied force this way. We have gravity down. We have the wall's response, right? The normal force pushing that way. And then we're gonna have friction up, right? Hopefully you can realize that if you push hard enough into the wall that the box is gonna stay stationary. Well, why? Well, because friction is gonna oppose this thing from sliding down. And let's look at it from a component form. In the x direction, we have the right force minus the left force equals 0. And we know it's equal to 0 because there's no acceleration this way or that way. So the two horizontal forces have to be balanced. And in the y direction, well, this is where I'm going to treat this as the positive y direction, because if there is an acceleration, it's going to be down in this case. And so I'm going to say mg minus the force of friction equals ma. I'm going to take this equation and solve for the normal force. So in this scenario, the normal force is equal to the applied force. So when I get rid of the force of friction, I can say mg minus mu times the normal force, but the normal force is Fa, equals ma. So look at this. How would you get an acceleration? Meaning, how would the box accelerate down? Well, it's going to accelerate down as if gravity is bigger than friction, the coefficient of friction times the applied force. If you don't push hard enough, this term isn't big enough, and gravity wins. And if gravity is bigger than this frictional force, well, then it's going to slide down, right? It's going to experience some sort of acceleration down the wall. But if you push hard enough, you can balance out mg and make it so there's no acceleration. All right, this is the hardest case, because if you push at an angle, well, you could see over here, if you don't push hard enough, the box might slide down. Now, if you push super hard, If you push horizontal, the box is not going to go up vertical, right? This is the maximum friction can be. Over here, if you push at an angle hard enough, you actually can make the box slide up the ramp. If you don't push very hard, the box might slide down the ramp. Well, if the box slides up or slides down, it's going to change the direction of friction. Okay, so let's end up doing 2 of these. Okay, version 1, let's have a really hard push. A really hard push. And so if we're going to push really hard, we're going to push with that applied force. mg is down. The normal force still opposes it, perpendicular to the surface. And if you push really hard, it might slide up. Well, if it slides up, then friction is going to be down. Okay, and let's kind of go through this. Horizontally, we have Fa cosine theta minus the normal force equals 0. There's no acceleration in the x direction, so those forces have to be balanced. And then vertically, we have Fa sine theta. That's the vertical component. Remember, if you push at an angle, you have this and you have this. Fa cosine theta is right here. Fa sine theta is up. So it's this up minus the force of friction down minus mg down equals ma. Again, if you push hard enough at a steep enough angle, this force up will be bigger than these 2 forces down, and the box will slide up the wall, right? It'll accelerate up the wall. Same thing we do. We know that the force of friction can be rewritten as mu n. N in this case, if you solve this equation, n equals Fa cosine theta. And so this equation down here becomes Fa sine theta minus mu times the normal force. In this case, it's Fa cosine theta minus gravity equals ma. And you might turn out that you're pushing and the box is stationary. Well, if the box is stationary or not accelerating, you just set this equal to 0 and then solve for something else. Okay? Now, if you have a really light push, you're still pushing but not as hard. Gravity is still pulling down. Normal force is still normal to the surface. But what would happen? Well, if you don't push hard enough, the box actually might slide down, and then friction would then be up. And so if you look at what happens, what does this do? Same, same, same. And all it would do was switch this sign. Okay, it would switch this sign to positive, or you could rewrite it and choose this to be the positive direction. And vertically, you could say, well, it's mg down minus Fa sine theta up minus friction up equals ma. Because if you're pushing really light, the box is going to go this way, and so we could call that the positive direction. Down versus the ups. If mg down is bigger than these 2 up forces, well, then there's going to be acceleration down the ramp. Okay, so those are kind of 5 examples with, this one having 2 different cases. Case number 1, Fa is really big, slide up the ramp. In case number 2, the box wants to go down the ramp, and so you can see how friction here is down and friction here is up. Okay, so that's scenario number 1. All right, scenario number 2 are all 3 just box problems. And I want to go over this first. You have to. This is an absolute requirement. There's no way around it. If you don't understand this, you will be super frustrated, and it makes everything else worse. Okay? So if you have a scenario where you have, well, again, we're going to go through the applied force first. If you have an applied force, I'm doing this in marker because this is super important. If you have an applied force in that direction, you are really pulling this way, and that's Fa cosine theta. But at the same time, you are pulling up, and that's Fa sine theta. We break down this vector based on the magnitude and the angle. So we do this all the time when you're like pulling a box. Well, the same thing has to be done when you start talking about a ramp. So if you look at a ramp, right, and you put a box on it, you have to break down gravity. We're going to tilt our coordinate system. This is our classic m and theta. We know that if the box can overcome friction, meaning the weight component overcomes friction. The acceleration is going to be this way. So we tilt our coordinate system such that the acceleration is in the direction of down the ramp. So instead of up and down and left and right, we have in and out of the ramp and up and down the ramp. This is the directions we're talking about. And so when you think about gravity, gravity is this direction. That length is straight up mg, just like this is straight up fa. But we need to break it down. Gravity pulls you down the ramp. That piece accelerates you down the ramp, and this keeps you on the ramp. Just like these two have pieces, these two have pieces. If this angle is some theta, then this is some other angle, okay? But that angle and that angle are the same, which means that this angle down here has to be theta. But if this angle is theta, this is the adjacent part. So that means this leg, the blue, is mg cosine theta, and the red is mg sine theta. So mg sine theta is the gravity's part that pulls you down the ramp. Mg cosine theta pulls you into the ramp. If you're good with this picture, then the rest of it is really easy because the normal force is just normal. It's straight in the y direction. Friction is just up the ramp. It's in the negative x direction. And so these forces then we're all going to look at. Okay, so let's look at this other one, this other picture. It's got all three ramp situations. Okay, ramp situation 1, box is just chilling on a ramp. That's it. Nothing difficult about it. Normal force is normal. Gravity is down. Friction would oppose it sliding down, so it's up the ramp. Again, we're going to tilt the coordinate system. We tilt the coordinate system like this. Down the ramp is x, in and out of the ramp is y. In the x direction, we have this component of gravity down the ramp. This part is mg sine theta. Up the ramp is friction. And that difference may or may not cause the box to accelerate down the ramp. In the y direction, we have the normal force out of the ramp. And then we have this piece of gravity, which is into the ramp. And that's mg cosine theta. Again, you're going to have to look back on the previous sheet that I had a blown up version. And that's equal to 0. Why? Well, because there's no acceleration vertically. Down the ramp, into the ramp. Gravity pulls them down the red and in the blue. This is sine, this is cosine. And that's not going to change. Look back on the previous example. This picture right here, you're going to draw it 1,000 times. Mg sine theta is down, mg cosine theta is in. The in will always end up balancing somehow or be affiliated with the normal force. This is going to correspond to the actual acceleration because this is about the force making it move. And again, we do what we always do. We take this equation here and we solve for the normal force. That's mg cosine theta. We're going to take this, and up here, instead of friction, we're going to write mu times the normal force, but the normal force is this. And so this equation becomes mg sine theta minus mu mg cosine theta equals ma. And does it accelerate? I don't know. Is this bigger than this? If gravity down the ramp is bigger than friction up the ramp, well then it'll accelerate down the ramp. You just have to tell me basically mu and the angle, and then I can tell you whether or not setting a box on this ramp accelerates down. Okay, let's add just a little bit. This is kind of sideways, but this says FA. This is some applied force. What if you were taking a box on a ramp and you were actually attaching a string to it and pulling it up? Well, we still have mg down. We still have the normal force perpendicular to the surface. Now we have some applied force vertically upward, but let's assume that this is big. So the box is going to accelerate up the ramp. Well, then friction would go down the ramp. And we do this same thing. What's making this thing move? This applied force. There's no angle associated with it because it's straight up the ramp. And what's opposing the motion? Well, friction is going to slow this thing down, and actually gravity is going to slow this thing down. Again, not mg, mg sine theta. The rope up, friction down, gravity's component down, that's going to equal ma. Again, if you pull hard enough that you overcome friction and you overcome gravity's component, well then you'll accelerate it up the ramp. Okay? Now if you were only pulling a little bit, not very hard, and the box was sliding down the ramp, well, we'd have to switch these things. This would be positive and those would be negative, and it would just be another case. In the y direction, we have the normal force, and we just have mg cosine theta. And nothing changes with the normal force in that case. There's no acceleration in this direction. This and this have no component, so it is just this. And again, we follow the same thing. We take friction, we replace it by mu times the normal force. The normal force is equal to mg cosine theta because we know this minus this equals to 0. And then we can write this whole thing that says Fa minus mu times the normal force, which is mg cosine theta, minus gravity down the ramp, mg sine theta, equals ma. And you can compare all of those things to decide whether or not it accelerates up and at what rate. All right, last one. I know this is a long video, but I want to kind of take you through all these different options. What if you were silly? Now, normally, if you're going to push a box up a ramp, don't you kind of like bend your knees and usually push straight up the ramp? But let's say you're really tall or you didn't really know how ramps worked, and you wanted to push straight horizontally. Now, if you push horizontally, you are going to accelerate this thing up the ramp, but you're also going to push it into the ramp. It's this consequence of the fact that you're pushing this way, and there still has a breakdown here. So we'll work through this scenario, and they put this on here just to kind of make it, this would be the hardest version. So you have an applied force this way, which is a little bit silly. You have gravity this way. You have the normal force that way, and you do still have, well, if it's going to go up the ramp, we'll say friction down the ramp. Okay, hang on. We're making a video, hang on. I have friction here. Okay, so we have to break, will you go tell the other two to be quiet when they come in? Thanks, bud. We have the applied force horizontally, and we need to break it down. That's easy, and we've already broken this down to down and in, but we have to do this. Okay, so if we draw this here, when you push horizontally, you're really pushing up and you're pushing in. Okay, pushing straight left is the same thing as pushing up and pushing into the ramp, right? Like if you pushed it hard enough, you'd like collapse this ramp. Okay, this is Fa. If this is the angle, that's the angle. So up the ramp is going to be cosine, and into the ramp is going to be sine. Again, you have to maybe draw a better picture than that. Maybe I'll do it right here in a second. But in the x direction, and again, when I say x direction, I mean up the ramp. Up the ramp direction is going to be Fa cosine theta. Fa cosine theta is up the ramp. Down the ramp is friction and gravity down the ramp. And that's going to equal ma, where a is the acceleration up or down the ramp. In the y direction, well, we have the normal force up, but you're pushing this into the ramp, so it's got this piece. So a minus Fa sine theta and a minus mg cosine theta equals 0, because pushing it in the ramp is not going to make it fly off the ramp at all. Again, this is the hardest problem. Break that down again. If that's your applied force, if you push this thing straight left, part of your force is going to make it go up the ramp, and part of your force is going to make it go into the ramp. See how this is horizontal? This is the same angle, which is why up the ramp is Fa cosine theta, and into the ramp is Fa sine theta. And you already got practice breaking down mg, and so if you look at this, the applied force is going to make it go up the ramp, friction's down the ramp, mg sine theta, weight is down the ramp, and if you push hard enough, even if there's an angle, you can still make it go up the ramp because this is bigger than those two, which causes an acceleration. The normal force is still in the y direction. Gravity, mg cosine theta, is still in, and then Fa sine theta is still in. And it's the upward in the y direction versus this force that are also balanced. And we would do the same thing. We'd replace friction by mu times the normal force. We would solve here, then the normal force is this crazy mg cosine theta plus Fa sine theta. And then we would take it and replace it and put it right here, and we get some mammoth equation that would say Fa cosine theta minus mu times the normal force, mg cosine theta plus Fa sine theta minus mg sine theta equals ma. That's a doozy, right? But that's the applied force up the ramp minus friction minus gravity, and that difference would then cause ma. Okay, that's a long video. I took you through almost every single individual box type scenario, but the process was the same. I went from a picture to a free body diagram to force equations. Every single one of these force equations was the same thing. I was looking at the net force and seeing whether it caused an acceleration. And again, some people don't like that. They like the sum of all forces equals ma. And some people even like to write it like this. The acceleration is equal to the sum of all the forces divided by mass. Hopefully this helps you out on your free body diagrams. This is kind of part one. Part two, we'll be looking at systems.